Welcome to this presentation on pole zero location based filter design method. In this video we will explain how we will calculate only one unknown in partial fraction expansion. We will map this unknown to poles and zeros, thereby completing the filter design. What are the reasons for filtering? Measurements are corrupted by high frequency noise which have to be filtered before processing. These are done by low pass filters which transmit low frequency information and remove the effect of high frequency noise. This is known as low pass filtering. Similarly, we can define high pass filters, band pass filters, etc. Some filters use slope information as well. To monitor transient response and to take corrective action, we require derivative action, and one can show that this requires high frequency content. All of these can be done by the choice of pole and zero locations. We will now explain how to design a filter using pole zero location. Apply the input u of k equals a power k into 1 of k, where 1 of k denotes unit step, to an LTI system whose transfer function is g of z. Suppose that we choose a equals exponential j omega, then this is equal to cos omega plus j sin omega, and hence this is equivalent to giving a sinusoidal input to this system. Suppose that gz does not have a pole at a. We want to know what happens to this frequency content when passed through g. So let us multiply the transfer function by the z transform of input. We know that the z transform of a power k is z over z minus a. So this is the corresponding output. Now let us expand this in partial fraction expansion. So we have a constant term plus a term that contains a root that contains a pole at z equals a, plus there will be some terms due to the poles of gz which we have not expanded. In fact, that is not required for this discussion. It is important to note that if E1 is made large, then the presence of z over z minus a will be present in output y, whereas if it is made very small, then the effect of the input is removed in the output. So let us start with the equation. And what is the expression for E1? Can we find E1 directly? Recall once again, if we use the simultaneous equation method to find the unknowns, we cannot do this because we need to know the poles of g of z also, that is the other terms also. Here we will use the Heaviside expansion method, which allows us to find specific unknowns. Not all the unknowns, we can find E1 alone, for example. Okay, to find E1, multiply both sides by z minus a by z and let z equals a, which is what I have done. And notice that the third term cancels the first term, we get g of z evaluated at z equals a, so it becomes g of a. So if you want to pass the input signal ak in the output, choose E1 large or g of a large. What do we do to make g of a large? This can be done if gz has a pole close to a, whereas a small E1 or small ga will reduce this input signal in the output. If E1 is made small or ga is made small, the effect of z over z minus a will be made very small. That is, it will reduce this input signal in the output. How do we make ga small? It can be done by having a 0 of gz near a. So from this we summarize that if I want to pass this input through, I need to have a pole at z equals a If I want to reject it, I need to have the 0 at A. Poles and zeros of which we are talking about the transfer function g of z, which is the transfer function of the filter. So if you want to pass a frequency, place the poles of the filter at that location. If you want to reject them, place the 0 there. Okay, let us repeat. If input frequency omega naught is to be passed through Gz, place poles of Gz near omega naught. If it is to be filtered, place zeros of Gz near omega naught. Remember that in sampled systems, unique frequency values are in this range minus pi to pi or over a length of 2 pi. And in this range, omega close to 0 corresponds to low frequencies, omega close to plus minus pi corresponds to high frequencies. Remember, pi itself is a high frequency, and remember the special property we had for real time signals, the symmetry property. This was discussed in one of the earlier videos. So omega close to plus minus pi corresponds to high frequencies, omega close to 0 corresponds to low frequencies. This range minus pi to pi defines a unit circle. So we have this unit circle, frequency close to 0 is low frequency, frequency close to minus pi or pi is a high frequency. It starts from minus pi and then it goes to plus pi. This defines the unit circle. We can show that the real axis portion, namely positive real axis portion, can be considered as low frequency, the negative real axis portion can be considered as high frequency. We will explain this in a subsequent slide. Let us repeat what we saw earlier, where to place poles and zeros. So you want to magnify or you want to pass through the low frequency information, you place poles there. So it becomes a low pass filter. Similarly, to reject high frequency component, put zeros there. So low pass filter has zeros at the high frequency locations. Similarly, high pass filter, you pass high frequency information and reject low frequency information. We have to remember to place the poles inside the unit circle for stability. We do not want to have unstable filters. For example, if the poles or zeros happen to be complex, choose them in conjugate pairs. Now we will discuss why frequency marking on real axis, low frequency and high frequency. Recall the impulse response we studied some time ago. Poles over here give rise to decaying signal, decaying response, whereas the poles on the negative real axis give rise to oscillatory sequence. In fact, they oscillate very fast, the sign itself keeps changing, and this corresponds to having the frequency of pi or minus pi, that is 180 degrees. This is the reason why we mark the positive real portion as low frequency and the negative real portion as and the negative real axis as high frequency. Let us conclude this video. This design method is available only for discrete time systems. You have to remember, however, that filter design is a huge topic. There are whole courses devoted to this topic, but notice that this method helps design a first cut filter quickly. Moreover, using this method, one can analyze filters designed through any other method. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.